This is about a new interpretation of quantum mechanics, global approximation interpretation, or standard interpretation. This talk is a brief reasoning version of the last video. Here's the outline. Firstly, the basic formulation of quantum mechanics is global, and this globality has profound implications, which has not been sufficiently discussed. We can understand many quantum behaviors intuitively from this global point of view. Secondly, quantum formulation is an approximation, and there's something neglected in the approximation. If we put back what has been neglected, we can understand the rest strange behaviors of quantum mechanics. We can even understand why Copenhagen interpretation resolved probability description from the approximation point of view. Now let's talk about the globality of quantum mechanics. The basic assumption of quantum mechanics, or de Broglie meta-wave assumption, implies everything discussed in quantum mechanics is a wave, and waves are global. Schrödinger equation is also global, because to solve the equation we need the knowledge of the entire space, including the potential and all boundary conditions. Any quantum or the wave function is also global. So everything in quantum mechanics is quantum and is global. Global means everything or every quantum discussed in quantum mechanics is a globally coherent wave. No one denies this globality, but this has never been discussed in detail. The significance of quantum globality is profound. One of the basic original assumptions of quantum mechanics, energy or angular momentum quantization, is the result of quantum globality, because global modes are discrete in bound systems. If quantization is a result of quantum globality, when we have some quantized property, such as the spin of the electron, we can reasonably presume it comes from some global effect, such as in interaction. Global coherence or correlation are naturally instant, because quantum or every object described by quantum mechanics is a global wave. We will also have global causality, because any local change is instantly global. This comes from the globality of quantum mechanic formulation, not necessarily the reality. We shall also keep other global effects in mind. Global causality is a particularly important concept in quantum mechanics. The causality we talked about usually means local causality from special theory of relativity, while any influence is limited by action propagation speed, which is the speed of the light. Local causality is common sense, physical, mandatory in all basic interactions. In quantum formulation, any local change has instant global effect, such as boundary condition. Quantum phenomenon has to be understood from the perspective of global causality. such as all interference experiments and quantum entanglement. And we can also understand why quantum entanglement cannot transmit information from this perspective. Information transmission needs local causality, but quantum entanglement only offers global causality, so quantum entanglement cannot transmit information. Many quantum phenomena happen in the global interacting environment, but not manifested in the formulation. When we talk about the lifetime of some atomic energy level or photon emission, it actually happens in the resonant system of many same-type atoms. In double-slit experiment, we neglected the fact that the whole system is bathed in an electromagnetic radiation ambience. The silver ion on the screen reduces even there's no light. This is important in understanding the particle-wave duality. Quantum mechanics formulation, or Schrödinger equation, is also an approximation, because Schrödinger equation assumes infinite action propagation speed. This is exactly the non-relativistic approximation. This approximation would lead to the instant establishment of quantum states, or if any change happens. In a real scenario, the establishment of a stable global state would take some time, and there are intermittent stages of revolution, such as action propagation, feedbacks, and iterations, until eventually reach the final state. Non-relativistic approximation omitted the evolution. However, in most quantum scenarios at atomic level, for instance, non-relativistic approximation is almost ideally valid. So quantum mechanics works perfectly in atomic scale. If the size of the system increases to a certain extent, such as long-distance entanglement, this approximation may no longer be valid. Non-relativistic approximation, or infinite action propagation speed, has more consequences than instant quantum state establishment. We already talked about the global causality. Instant establishment also means the details of physical processes, hence physical interaction, is lost. The whole process is abstracted. Schrödinger equation gives the ideal abstract description of the evolution of the system. And the solution to Schrödinger equation, or the wave function, becomes virtual and dimensionless. The loss of quantum state evolution, or instant quantum state buildup, or change, also lead to probability description of measurement collapse of wave function, because there's no way to track the evolution of the system. We can also find the line between the quantum and the classical world is whether non-relativistic approximation is valid or not. Of course, we are talking about the dominant interaction. If non-relativistic approximation is valid, the system is quantum. And if not, the system is classic. And if in between, the system is kind of decoherent quantum state. Now we have the global approximation interpretation of quantum mechanics. It says quantum mechanic formulation, including Schrödinger equation and its matrix form, is ideally global and non-relativistic approximate. They work well in small, strongly coupled systems. As system scale grows, or less strongly coupled, the system turns local and classical. Put what omitted back, we can interpret all quantum processes intuitively, including quantum eraser, which by global causality, and quantum entanglement is also from global causality, and atomic energy transition is mostly global resonance. We can also understand why Copenhagen interpretation resolved to probability description of wave function and measurement. Global approximation interpretation can answer more quantum-related questions. Please refer to our paper, which is listed in the description of this video. Thank you, and please subscribe.